I'm not sure if there's so few because I expected a read or because you didn't expect me. I'm going to continue. Is it your own here? Okay, so actually I talked about many things last time, and I'm sure you have a lot of questions. If you don't, I'll be surprised. If you just try to somehow organize it for yourself. So I just want to take a few minutes just to remind you what we're talking about. So we started to talk about what we call typical patterns. Now, usually in information theory, they usually talk about sequences, but I want to think about more general things, not necessarily functions of time. So we assume that there's some random variables, which can be many, that are not entirely independent. So I can index them as a sequence, or I can index them in 2-dimension or 3-dimension. It doesn't really matter, as long as it's a countable set. And it's and when we talk about the probability of these things, so this is a special case of what we sometimes call stochastic processes. So there are many variables which may or may not be related to each other. And there's a whole theory of such models which are multiply connected in complicated ways. So it goes in general under the more modern names of graphical models, graphical statistical models, or an equivalent, or not exactly equivalent, but very strongly related thing is what we call Bayesian networks. And these are very closely related to what we call neural networks. So in some sense, neural networks are special cases of graphical models, and the Bayesian networks are graphical models with some Bayesian interpretation. But these are all similar things. And what we call neural network here is a special case of what I call neural networks, which are neural networks of biological nature. So I just want you to, and in general, the way we think about these things is some sort of graphs, where the nodes of the graphs are variables, x1, x2, x3, and so on, x4. Can have and the edges or the connections in the graph are related to statistical dependencies. So okay, so this is just just to give you some idea what we're talking about. It's not the many books, several textbooks on graphical models, and we actually have courses on graphical models. So this is a very useful way of thinking about dependencies of variables. And so for example, in this graph that I just drew, it's a special case of graph that we call a planar graph, because I can actually write it in a plane. And it's an undirected graph because I didn't put arrows on the connections. But I can always think about graphs as directed graphs by directing them one way or another, something like this, for example. So this will, now what we mean by this is that if given a graph of variables, we can actually write a joint probability distribution. So essentially there is some sort of correspondence between probability distributions of multiple variables and graphs like this. So essentially, so as I said, the arrows correspond to statistical dependencies. So if let's say there's another node here, x17, which is not connected to anything, this tells you that it's not connected to anything, which means it's not there's no dependencies, no statistical dependencies. So it's essentially another independent variable. If they're all independent, then we don't have any arrows, any connections, any nodes. Okay, so if you know something about graphs, so graphs are those objects which are defined by edges and nodes in general, and there are many things I can tell you about graphs, but the only thing you need to know right now is that there is, so we talk about connected, there may be two connected pieces here. Okay, so this, for example, it's another independent graph, but if they're not connected with arrows, they're actually two different independent models. These variables don't talk to each other. And so the intuition or the formal mathematics behind the graphical models is essentially telling us, okay, so I told you that in general I can factorize a joint distribution in essentially n factorial ways. Just like conditioning on the previous things, we saw it already. But if there are connections, if there's a graph, so many of those dependencies becomes redundant. So essentially, each variable depends only, so for example, x3 here, depends only on what we call the parents. So if it's a directed graph, it's only those nodes that have arrows that point to x3. If it's undirected graph, then essentially everything that connects to it can be its parents. So in this case, I actually assume that x3 is affected by x1, x5, and x4. and x2 is affected only by x3, and x1 is affected only by x2, and so on. But if I don't have arrows, then in principle they can affect each other. So x1 is affected by x2, and x2 is affected by x1. So undirected graphs mean that the dependencies can go both ways, and directed graphs actually implies one particular connection, one particular direction, which means that if I now write the joint distribution of the variables, I always have to condition only on what we call the parents of the variable. So the parents of the variable are exactly all those things which affect him. So I can think about many graphs, for example, polygenetic graphs, families, genealogical graphs. So a graph like this is each one of us has two parents, which may have other two parents, and so on. And I may have many children, but and so on. Okay, so this is me, and this is my father and mother, and we usually think about it as a directed graph. Okay. So this is a very important type of graph, genealogical graph. I can have a similar graph, which is my academic tree, for example, all my students and all the people that influence me, and so on. So we also talk about graphs like this. Or we can talk about transportation graph, all the roads that connect cities or connect places, and so on and so forth. Graphs are graphs. In general, graphs are not that simple. They can be. So one thing that we usually, when we start to somehow think about graphs that have special properties, so some graphs that have special properties are, for example, trees. So trees are graphs that have, let's say, one root, and then each node only has sons, which may be several or none, and so on. So this is a tree. So a tree is a directed graph which has a root. It's actually the opposite of what you think about a tree. So a tree actually is two graphs, the roots and the leaves, which is another. But so this is just one side of the tree, and so these are trees. Okay. So trees are directed graphs with some structure like this, that each one only goes. So what is special about trees is could you see it? And so what's special about trees? So they're directed graphs, but they are. Yeah, there's a hierarchy. There's a natural hierarchy. So there's a root and first generation, second generation, and so on. And there is and there's something which is not there. There are no cycles. So in some sense, I cannot have this in a tree. So in some sense, it's so this is not necessarily a cycle. It's a cycle only if it's undirected. If I actually arrow it like this, then it's not a cycle, in the sense that, but it's still what we call head cycle in at least in the undirected sense. So there are two ways to get to this. In a tree, there's only one way to connect every two variables.
You mean there's no convergence?
No. So in this case, so a tree is actually defined as a directed graph with a single path between every two variables if it exists. And for example, if I want to connect this one to this one, I have to go back to the root. So if these are my two cousins, or something like this, cousins are second generation relatives, and so on. Okay, so this is a tree. Now, sometimes we talk about directed acyclic graphs. So directed acyclic graph, which in computer science we like to call them DAGs, or directed acyclic graph, is a graph which is directed, and after the direction, for example, this one was a directed acyclic graph, despite the fact that there is a closed loop. There are two ways, but it's acyclic. But if I'll direct it that way, then this is a cycle. which means this affects this, this affects this, this affects this, and this affects this again. So there are cycles are headaches. I mean, these are feedbacks in some sense in my system.
It's possible that two converge to the same one. Is that possible?
No, a cycle here is this when I arrow it such in a way that I can actually I have a cycle of influences.
Yeah.
Okay. So
Can you repeat this?
if they're both if it's this way, there's no cycle.
Okay.
So a dog is more than a tree. A tree is a dog, but a dog can have multiple passes between variables, but no cycles. Okay, it's directed, and then we talk about so acyclic graphs are much easier to handle because there's a unique way of factorizing the distribution. So if they're acyclic, then there's only one way of factorizing a joint distribution. Okay. So in general, I can always write, given a graph, I can always write the joint distribution as a product over all the variables of the probability of variable condition on what we call the parents of the variable. And the parents are exactly those that directly affect him. Okay, so it's a very intuitive thing. So I'm directly, my genome at least is directly affected by my parents, by the genes of my parents. My behavior is probably affected by a few other people as well. But so these are my parents, those that are directly affecting me. Okay? Yes? Yeah, there are many. If I'm going to teach you a full course on graphical models, it will take me too long at this point. Well, the graphical model is a graph with a probabilistic interpretation. Essentially, it's as I said, it's a set of random variables where the distribution of the random variables can be factored according to the laws of the graph, which means the dependencies are only the arrows that are connected to it. Now, one of the basic theorem of graphical models is that I can always take an undirected graph and turn it into a DAG, a directed acyclic graph, by finding the arrows in the right direction. Okay, which is good, because DAGs I have a unique way of factorizing. Okay, so that's good. So one of the basic things that we want to do if we see an undirected graph in general, so we have connections and we don't know what is affecting what. So affection is something that has the flavor of causality. I mean, what is affecting what? And causality is a very big headache in statistical models in general. I mean, we don't really know how to define it properly, and there's a whole line of literature about how to infer causality from data. But it's, among other things, when I turn an undirected graph into a directed graph, I actually assume or induce some causality. So this is affecting this, but so the genome of my father affects me, but my genome did not affect my father, as far as I know, at least. Maybe all sorts of epigenetic things that can affect us eventually in life, but it's not the way we think about genomes today. So yes.
In Bayesian networks, you can, I think, if you have one arrow, you can always have the arrow to the other side, the other direction.
Yeah. So Bayesian network. So again, there's a zoo of theorems here, but essentially, yes, I can always direct a graph, and there are many ways of doing it. There's not
every arrow has the arrow to the other direction, the Bayesian rule.
No. Okay, so you're right, but I'm breaking Bayesian. In some sense, when I direct a graph, I think only about one way of conditioning and not the other way. You're right. So Bayesian networks, if I'm not Bayesian, then I want to direct it in the right way. So I can infer from theta to x, but not from x to theta. And you're absolutely right. I mean, Bayes' rule is a way of inverting the arrows. But so anyway, if I'm talking about directed graphs, then the calculus of probabilities in a graphical model is more or less straightforward. When I have cycles, then I'm getting headaches. I mean, what I mean headaches? If I fix the probability of one variable, it may not be final because it can be influenced by something which I haven't determined yet. So I'm going to have these feedback loops. And in general, solving the inference problems or in graphical models, which is what we want to do in most cases, is done by directing it first and then write some sort of a likelihood function over which we assume what is known and what is unknown, and then we do EM or things like this. So we already saw several graphs. I mean, Markov chain is a very simple graph. x1, x2. And as you see, in a Markov chain, I don't worry too much about direction. I can direct it usually in both ways without causing cycles. It's not a problem. If I have, for example, I don't know how many of you learned something about language. So parsing trees of sentences are some sort of graphs. And they're usually generative models that are actually trees. Yeah, so they are undirected and cycles less. They are not even dogs. But sometimes they do. I mean, sometimes we have different interpretation of the sentence depending on how we parse it, which means there are different dependencies between words. So this is one example where we use graphical models all the way in analyzing natural languages or things like this. Yes?
Well, why should you say that the factorization here is the most...
So no, I can always write, this is a factorization. The question is it a unique factorization? Is it unique? And if my graph is directed and acyclic, it is unique. Okay, there's only one way of factorizing the distribution. Okay. Now I showed you, or at least I mentioned already, several other models. For example, so this is a Markov chain, which in principle can go forever in both directions. I can have what we call a hidden Markov model. So the states, these are the states of a Markov chain. And sometimes they're written by S, not by X, but that doesn't matter. And then I can have an observation, let's say 1, Y1, Y2, and so on, in every one of those. So this type of graph, a Markov chain with an observation which depends on my state, is a very important model. This is actually some sort of a tree. It's a tree. But it's a tree only if I know all the states. But if I don't know the states, so it's a tree with only one split at every generation, and that's it. So it's a very special tree. But it's if X are unknown, this is known as hidden Markov model, or HMM, which are quite important in this business. So this is modeling a sequence when there are underlying hidden states. This is usually the graphical model of a hidden Markov model. Now we can have a different model I was mentioning. For example, if we have states, let's say states of the world, W1, W2, and so on. Usually I don't have the energy to write the circles around them. So assume that there are circles, it doesn't matter. So this is, for example, a Markov chain which can be the world state. The world can be anything from the state of one atom to the state of the universe, but it can be anything. So, or one electron, whatever you want. Anything that, so a state can be very complicated, but at least what physics tells us that if I know the state of the universe now, it completely determines the state of the universe in the next time. So the universe in principle is a Markov chain. Okay. Unfortunately, we don't really know the state of the world at any time, so it's very much hidden. But which makes the inference. So for example, in a Markov chain, in order to make predictions, I only need to know the previous state, because there's no dependencies further. But if in a hidden Markov state, if I see only the y's and not the x's, so the hidden observations are not Markov, because they depend on much further. So y2 depends not only on y1, because it may depend on y0, or y3 depends on 1y and 1, 2, and so on. So there's infinite memory actually in a hidden Markov state. So it's a much more complicated sequence. So speech, for example, is usually modeled by hidden Markov models. When you think about it, there are hidden phonemes or hidden words or whatever, and what we see is the sound or something like this, which is a stochastic observation of the hidden states. Okay. Now another model is something we call Markov decision process, which I just want you to all remember. So in the Markov decision process, we actually see the state, and then we make, so we see the state directly, and then we make an action. No, I want to call this the memory. And then we make an action, which is another variable, which affects the state of the next state of the world. So but in general, we don't really see the state. We see something which we call observation of the state. And this affects our memory, and this generates an action, and so on. So this is already a more complicated model, which is the Markov decision process is when it's a fully observed state. I actually see the state of the world. In reality, even in very artificial setups, this is not always true. We don't really see the state of the world, although I can design experiments in neuroscience or wherever, where I assume that I see the state of the world. The world is limited. But if I don't see, then I have what you call partially observed Markov decision processes. So this is Markov decision processes, and this is partially observed Markov decision processes. And partially observed means I don't really see. So this O is a noisy observation of W. So this is some sort of a combination of an HMM with an MDP. I usually write it like this. This is HMM plus MDP. And this is HMMs are hard in some sense. I mean, the inference or the prediction of the observation in an HMM is very difficult. It's actually NP hard. And MDPs are actually easy. There's an optimal way of solving MDPs, at least if the model is known. It's called reinforcement learning or optimal control, or it has many different names that you may have seen all over the place. But if I hide the state, then all the difficulty of HMM pops again, and so POMDPs are hard again.
So then W is hidden?
Yeah, W is hidden. And by the way, if I have memory, then my memory state may affect the memory state the next time. So if this is time, and then I have the full-blown POMDP. I mean, so my memory states affect. Now, this is a graphical model, which means that I have to assign probabilities to every one of those nodes. But it's giving me a factorization of the probability distribution in terms of this Markov. So this is just a very complicated Markov chain, because these four variables can be thought as a state which evolves Markovian in time. This is a very popular model. We are using it all the time in modeling neuroscience, or in modeling behavior, or in modeling cognitive functions, whatever you want. It's very important for us. Now, and of course, there are many, many other models. For example, if I want to model an image, a picture, or a two-dimensional image, then a very common model is what we call Markov random field, which is essentially a two-dimensional Markov chain in some sense. So it's a Markov random field, or an MRF, is essentially a two-dimensional chain of variables which lie on a grid, so this looks like a very much undirected graph. But each variable has neighbors. So in this case, for example, this variable here, this pixel, these are its neighbors, and so I can direct it in various ways. But directing an image doesn't make too much sense in general. I mean, there are many ways of a sequence in time. Okay, makes sense. There's some sort of causality. But in directing an image, you need to choose some sort of influences, and usually we don't want to do it. So, but there's two parents. So the parents of this variable are only those nearest neighbors. Actually, it's only these four. Yeah, that are directly connected to him, and so on. Okay, so given a graph, I can factorize the distribution. That's important. And then I can do all sorts of things. Now, the reason I mentioned it, first of all, I want you all to remember those models. We're not going to do much with them. I'm going to talk a little bit about trees later on today. But we're not going to, unfortunately, I actually wanted to solve with you. So, for example, clustering, just mixture model, like general Gaussian mixtures or things like this, which Ravit started to talk about and didn't quite finish. So this is a very simple graphical model. We have X, which is, or the clusters, and we have the Y, which is the observations. So this is all the graph. But essentially X is a variable that takes the values of the clusters. And given the cluster, so for example, this particular, if this is the Gaussian distribution and X is some parameter of the cluster, this is just a Gaussian mixture model. So even complicated model can have very simple graphs. It doesn't really change much. Yes. Okay.
How can I know the correlation between the graphs?
So once the graph is given, I need to direct it somehow. So I can choose some arrows. So as I said, there's a theorem that I can take an undirected graph and always orient it, direct it in some way, without cycles. So this is a choice of influence. Essentially, if sometimes nature dictates it, like causality in time or things like this, and sometimes not. Sometimes I have to choose if to direct it in one way or another. So I usually pick one, and actually then I can turn it into a tree. So if it's undirected without cycles, I can turn it into what we call a junction tree by defining new variables. So every undirected graph can be turned into a tree, what we call a junction tree graph. And a tree is very nice. A tree is very easy because there's one path that connects any two variables, and there's no way I can confuse myself in any way. But this is exactly where the graphical model course is taking you. What is important for me is that if such factorization exists, and as I'm essentially trying to tell you, models with unbounded degree, which means there are many the number of arrows that point to every node is not bounded, this can be extremely complicated. So usually we assume that there's a bound on the degree of the graph. And if there's a bounded degree of the graph, then I have what I wanted to say last time. I simply didn't elaborate. So we have this factorization, and I know that the cardinality of the parents is bounded by the degree of the graph. The degree, by the way, is the number of edges that comes to a node. And if this is bounded, let's say by some number d, then the number of variables that appear here is most d. And then the thing looks very nice, because then the log of this.
What's d again?
So d is the degree of the graph, which is the maximum number of edges. Something doesn't look right here. Maximum number of edges. So it's
Edge in the graph?
So I said a graph is a collection of nodes, which are the variables, and lines that connect them. And the lines are the edges, and the nodes are the cycles, the variables. Okay. And actually, on every edge, there is some sort of a conditional distribution. How this end of it depends on the previous one. But actually, so in general, I can write it like this, and if these probabilities are fixed, I mean, they don't depend on I here, then the log of it is going to be simply the sum. This is always true. Now, if this has bounded complexity in the sense that the number of possible terms there is at most d plus 1 or something like this, then this eventually is going to average. If I take 1 over n here and put a minus here just to make it positive, 1 over n log of this, this is minus 1 over n this, and this is now very much a sum of independent terms. So they're condition independent, but each one of them, when I condition, become independent. That's the power of conditioning. So, so this is going to converge. And very general conditions. It's going to converge to what I call the generalized entropy of the X. So this is the entropy. So this is the entropy of a source, or the entropy of any general connection. Okay. And now I actually told you, okay, so the
limit is on n?
Yeah, the limit is on n, yeah. When n becomes large, this converge in probability if you really want to be strict. But okay, so the point is that I'm looking at any collection of variables which are connected through any graphical model with bounded degree at least, and they're going to behave nicely. Actually, I can even relax this bounded degree to something weaker than this, but this is good enough for us at this point. So, so this is what I'm going to call the entropy of the graph, the entropy of the pattern, the entropy of the source, or whatever. This particular number, if it exists. And of course, it exists because of the standard observation that some of independent things, if they are bounded and so on, with some restrictions on what this can be. I don't like zero probabilities there, but otherwise it's okay.
Well, why is it so important that they are bounded? The graph is bounded.
No, what do you mean? The degree is bounded.
Yeah.
No, because the degree is not bounded, then you can get again and new terms here all the time. I mean, and those are not going to average. I mean, you're going to get combinations which you haven't seen before all the time. So in order for this to average, I need to eventually sample all my a finite number of configurations.
If you have finite number of nodes.
Sorry?
If you have finite number of nodes.
A finite number of nodes.
And still
Yeah, okay. And then it's in some sense not interesting. Yeah, you're right. I mean, so this is an asymptotic. It has an asymptotic theorem in some sense. I mean, so even if you have a finite number of nodes, but you can repeat going in them, something like a finite state machine, but I keep on, like a Markov chain with finite number of states, but I always keep on going, then it's the sequence in time which matters. I mean, so the identities can indeed repeat. So finite number of nodes is good. But the point is, in order for this to be true, that this converge to a number, you need the usual trick. I mean, I take a big sample, or the big sequence, and divide it into the number of times that I saw a certain configuration, which means the number of times that this node appeared after these parents. And only then I can actually say, okay, the number of times that this appears in my sequence is proportional to the probability. And this will converge to the probability, log probability, only when you have enough of this. So if you have an unbounded degree, you're always going to see new things. By the way, this is a serious problem for things like language. I don't know if you know, but in language, we always see new things. I mean, the number of words is unbounded. Not to speak about the number of sentences. Yes? Sure.
The number of sentences.
No, number of sentences is, if the number of words is bounded, the number of bounded size sentences is also bounded. Of course it is. Bounded. No, not finite, bounded. I mean, if I tell you that I can have at most 100 words in a sentence, which is a very good bound for most sentences. Of course, there are some books without a colon. Also, some of the books of one of my favorite writers, it's one sentence. Okay, that's all right. I mean, this is unusual, but in a normal language, the number of words in a sentence is bounded. It's not finite; it's bounded. You can have unbounded but finite sentences, which means that every sentence has a finite number of words, but this number is unbounded. I mean, it can grow forever. So this is what Chomsky said about languages. It's not true in practice. I mean, most people don't speak with unbounded sentences. I mean, we actually have very small number of words in a sentence in most cases. And I think that 100 words per sentence is a very good bound. If I truncate every sentence after 100 words, I am not going to lose much of the language. Okay, so it's actually enough that the length of the sequences is decaying not even exponentially, but converging, that I'm already okay. I mean, but what is much more important is that words, the number of words is not bounded. There are always new words. I can assure you that if you read the Israeli newspapers, every day you'll find words that haven't been there, never appeared before. Surprising you?
No, but
Actually, I can show you. Just that, I know it's a bit a sidetrack, but never mind. If you look at, you count the number of new words, or the number of words that never appeared before. Okay? Whenever you see a word which is new, never saw it, as a function of the number of words that you read. Okay, so take a text, any text, any natural text. I mean, text the New York Times, I don't know, any newspaper or anything, except artificial languages, which are not, but anything which is natural, and you look at the number of new words. So new word, just start counting strings between spaces or between punctuations. And whenever you see a new string, which never appeared before, you increase this counter. Okay? So the surprise is that this grows, and it actually grows very much like a power law. I mean, it grows like close to the square root of number of n. So this is the number of words that you read. Graphical statistical models are 3 words, and so on. Okay, whenever you see a new word, you increase the counter. So something which linguists tend to ignore completely, but simply because they don't understand it, it's actually very easy to explain, is that the number of words grow like a power law, and it actually grows like n to some power, and this power is something between, it's usually greater than 0.5 and less than 0.7. And for all languages. Never saturate. Try it yourself. You can try it at home, it's not dangerous. Simply write a short program that runs on text and count it. So this is something I always like to show my students, and they never believe me. And it never saturates. I mean, you count 1 million words, it's still growing. You count 1 billion words and still growing, and so on. And the power is extremely constant.
even if you use only text from a certain point in time and you run it without updating the new words investing in
If you don't update the new words, then you're not using a natural language. What do you mean? And what I'm actually saying that a language is a living organism, and it's always generating new concepts in a constant rate, and this rate is this exponent. And but this is actually a problem for a graphical model that describes language, because it means that the number of nodes is growing. So you have to think about different models, but that's a different story. Yes. I wasted an hour. Okay, yeah. Go ahead.
Isn't the degree of the graph bounded anyway by the number of nodes?
Yeah, the degree, if the number of nodes is finite, then the maximum degree is the number of nodes. But we think about it because you cannot connect to more than all the nodes. Yeah. But usually we think about n as growing to infinity, but the degree is finite. So we think about the sequence in time. So that's why this limit is n goes to infinity. So indeed, it's the number of nodes, and the number of nodes can be indexed by time, for example. So when you think about a typical image, I'm actually thinking about really a lot of pixels. And it doesn't really matter if I sample this as a megapixel or 10 megapixel or in a gigapixel. It will look the same image more or less. Okay, so there's some sort of limit here. This is an asymptotic. So entropy is indeed an asymptotic thing. And this is simply, again, because this is simply going to be minus the sum over all these xi, over all these tuples of xi and parents of xi, of p of xi given the parents log of this. Okay, this is already. But this is why it's entropy. It's converged to the entropy precisely because I can sample all these things many times. Good. Okay, then I actually state something which is usually known as the asymptotic equipartition property. And I don't know if I told you this name, AEP, or asymptotic equipartition property, which was extremely important. So essentially, the way I did it, I said, okay, if we have a regular model like this, which is precisely what I mean by a regular model, or a structured pattern, then I defined something which I called A epsilon n, which was the set of all the possible sequences of size n. By the way, I always assumed here that x is somehow finite. So there's a finite alphabet, or there's a finite number of letters in the language, or a finite number of words. It's not, as I said, I mean, there's some atoms in my program which has to be finite. It can be even binary, but it doesn't really matter. So these sequences, and I define them as all the sequences such that the log probability of the sequence, or minus the log probability of the sequence, is greater than the entropy minus epsilon and the entropy plus epsilon. So this set is a set which depends on n and epsilon. Essentially, you see that essentially I'm just, so what's happening here, I said it already last time, and I know that I need to take a break, but just a second. Essentially, this is converging to a normal distribution. This is the whole story. And since this is converging to a normal distribution, if I pick an epsilon, it's converging to the entropy with high probability. Now, if I pick an epsilon below the entropy and epsilon above the entropy, these logs are going to converge exactly to the entropy, the average log. But if the standard deviation, or the width of this Gaussian, goes like square root of n. Okay, this we saw many times. This is the whole point. This little n is the same as this big N here. That's the same thing. Okay, so this is going to converge to a Gaussian with shrinking width that goes like 1 over square root of n. I'm sorry, like 1 over square root of n. Yeah, if I normalize, it's 1 over square root of n. So this means that if I put an epsilon, there exists an n which will put most of the Gaussian within epsilon away from the mean. Okay? So what this means, it's that for every epsilon greater than 0, there exists an n of epsilon such that for all n larger than this n of epsilon, this was a statement I mentioned last time, the probability of A epsilon n is greater than 1 minus epsilon. So this is the theorem, which is known as the Shannon-Macmillan theorem. It's actually not really Shannon, it's called the typicality theorem, or the asymptotic equipartition theorem, AEP, which actually tells me that give me any positive epsilon, there exists n large enough such that the probability of being outside this epsilon away from the mean is smaller than epsilon. Okay? And it's clear why. I mean, it should be clear to all of you. Although this is not an entirely rigorous statement, it's still true. This is going to shrink. If epsilon is 6, I can always wait until the tails are less than epsilon. Okay? So it's kind of epsilon n argument, exactly as you see in many other places. But this is very important, as I said before, because it means that eventually, for large enough n, all the sequences, or almost all the sequences, are going to be in this set. And not only that are going to be in this set, all the elements in this set are going to have the same probability. Okay?
Okay.
חד חלקי n. תודה. Okay. So it's not only that, for every, so this is what we call the typical patterns or sequences that are those in this set. And eventually all of them are, almost all the sets, the patterns are typical. Okay? This is what it means. Okay, so this is really very important. I'm going to stop here. I said one other thing. So what is going to be the probability of a typical pattern? Well, it's written here. I just have to invert it. So this is just like saying that the probability of this pattern is essentially up to this asymptotic correction. 2, if this is log 2, it's 2 to the minus nh, plus or minus epsilon. Okay, so if epsilon is small enough, this is essentially 2 to the minus nh with some correction, which scales with n. So essentially, all those patterns are equally likely. They have the same probability. So what is the size of the set? So if this was a discrete set, if you have a set of equally likely objects, what is the size of this object? And that's distinct, of course. What is the size? 1 over this probability. So the size of this, like saying that the size of this set, the cardinality of this set, is essentially, again, after this asymptotic correction, is essentially how much? 1 over the probability, which is 2 to the n Ajax. Okay, so I'm going to stop here, and then after saying that again, I just wanted to, I'm going to go back to what I promised you last time, which is data compression. Start to talk about data compression. Okay, so let's take 10 minutes more or less. I'm back. I hope that Ravid will be okay next week, but I'm not going to miss any class. If he's not here, I'm here. אני אומר שמספר המילים בשפה הוא לא פסיכי, למרות כל מה שכל מיני אנשים צריכים להגיד. אין דבר כזה. כל הזמן עשרות מילים חדשות.
כן, שאלה באיזה זמן,
אז אני אומר, בדיוק זה פונקציה של אורך מספר המילים, זה פונקציה של השימוש בשפה. כמה שאת רואה יותר מילים.
אני יודעת אוסף מילים. אני יכולה לייצר משפט אינסופי, איזה סנט.
כן, גם לא יודעת מספר המילים. אפילו אם רק תדברים לפני. כל חיי תייצרים מילים חדשים. מהסיבה הפשוטה שאנחנו מייצרים ברגע נתון יש לנו מספר סופי של כל דבר בעולם. אבל מספר המילים, לא, אבל אם את שואלת כמה מילים יש בעברית, אין לזה שום תשובה. לא, זה גדל קצב קבוע. מסתכלת על לוג מספר המילים השונות.
אבל יש כאן המילים נעבוד
זה פונקציה של לוג מספר המילים, זה נראה פונקציה מספר המילים.
מה שאני אומרת שהמשפט הוא איכות שונה של האמבט של מילים. כי אתה יכול להגיד עם
האמבט משפט זה כמו להגיד
שרוני חושב שיוסי חושב ולהמשיך ככה. וזה מבחינה אחרת
זה רעיון להראות את זה שתלרות אבל לבנות שזה כאדם טבעלי הוא שאל אותי בין את השאלה הזאת הוא אומר לי כן, אבל יש למרות שמספר סופי של פונמות ומספר סופי של מילים יש מספר אין לזה של סופי
זה לא אמרתי שזה מספר אמרתי שזה יכול לייצר משפט בעוד חנסופי
אני לא יכול לעשות מספר באופן סופי בזמן סופי אבל אני נותן שחייהם מוגבלים אז אני לא יכול לייצר מספר לא, זה לא אקספוננציאלי. זה גדל כבר מספר סדרות של הבינארית, אוקיי? נכון, זה גדל אקספוננציאלי. מספר המשפטים האפשריים באופן גדל אקספוננציאלי. זה לא אינסופי. אבל מה שיותר חמור מזה שמספר המילים הוא אינסופי. זה לא חשוב. לא, זה הדברים, זה מה יותר מעניין. זה שמספר קונפיגורציות של K אלמנטים הולך כמו K שחקן N, זה אנחנו יודעים גם בלי הפונקציה. לא צריך לבחון כזה. לא, זה טריוויאלי. אם אני יכול לייצר משפטים ארוכים פרסומים, אז אני יכול לייצר משפטים. אבל כל החוכמה היא, הדקה, זה שאנחנו לא משתמשים במשפטים מאוד ארוכים, רוב הזמן. המשפטים הארוכים מאוד הם נדירים עד כדי negligible, ויחד עם זה אנחנו רואים דברים שהם המשמעויות, הם שואלת אותי כמה טקסטים שונים אפשר לייצר, שזה גדל אקספוננציאלי לאורך הטקסט. זה שוב, טענה טריוויאלית. עכשיו, הדבר המעניין זה שאנחנו מייצרים מושגים חדשים כל הזמן. כשאני נכנס לכתיבה חדשה, אז אני גם מציין מילים חדשות. והשאלה המעניינת זה מה אותי פחות מעניינת, זה מה שולט על הקצב של יצירת המילים החדשות. מה קובע לנו שיודע, בשפה מסוימת יש 3 מילים לצבע, בשפה אחרת יש 40 מילים לצבע. בדיוק העבודה של נוגה, אמרת עכשיו שולחת היום, בדיוק העניין הזה של להגדיר את היעילות של... למה ככה יפן? לא, עכשיו הסתכלנו על 200 ספורט. שאלנו מה מייחד את המספר הצבעים, המילים לצבע בספורט שם. זה דווקא מקרה מאוד מיוחד, שכתובות צבאי שלי, שיש רגולריות מאוד גבוהה ביצירה של מילים חדשות, שזה נראה בערך כמו איזשהו מהלך מקרי באיזשהו מקום. אז אתה מגיע לאזור שלא רואים קרובות, אבל אתה מייצרת מילה חדשה. והקצב הזה של מילים חדשות זה קרוב.
בכל חברה?
בכל אוניברסלי, לא תלוי בשפה, לא תלוי בחברה, כמעט. כמעט אומרת, זה כמו הבדל בין 0.5 ל-0.7 באקספוננט. יש הבדלים קטנים מאוד. כן, זה אחד מהם שאנחנו מנסים להסביר. אבל זה דבר הרבה יותר מעניין מבחינתי עם העובדה שיש אינסוף משפטים, כי אין דבר אחר. אינסוף משפטים זה כמו להגיד, יש אינסוף ספרות.
זה לא להגיד שיש אינסוף משפטים, יש משפט.
אין משפט.
פוטנציאלית יכול להיות.
זה פשוט לא נכון.
החוקים מאפשרים לך.
יש הבדל בין להגיד אורך המשפטים לא חסום, להגיד יש משפט אינסופי. אורך המשפטים לא חסום זה טענה חסרת משמעות. לא, זהו, זה לא נכון. כי הפילוג של אורכי המשפטים יורד לאפס לאורך סופי מאוד מאוד מהר, אז למה זה זמין?
אבל אתה מדבר פה על נתונים אמפיריים.
לא, נתונים אמפיריים. לא, אני מדבר על המודל עצמו, זה קשקוש. כי זה כמו להגיד, אם אני מקצץ לכל המשפטים באורך 100 לא השאתי כלום מהיכולת לשנות. כלום. אז היכולת לשנות שלנו, היכולת לשנות את העומק של השפה, התכונה הזאת המיוחדת של השפה האנושית, לא יכול להיות תלוי, לא יכולה להיות תלויה ביכולת של לייצר משפטים אינסופיים. כי אין משפטים אינסופיים. אז לשים את... לא, זו תכונה מטומטמת. סליחי לי, אני לא למד בשלות. לא, אני חושב שבלשנים מקובעים בעניין הזה. משום שזה בדיוק כמו להגיד, כן, יש לנו אינסוף, מספר אינסופי של סידורים של אטומים בחומר, ולכן יש אינסוף חומרים. לא נכון. עכשיו, זה...
אבל אתה עדיין יכול לייצר משפט, דברים לא יצרו, כולם יודעים אותו.
זה שאלה אחרת לגמרי. כל הזמן מייצרים משפטים חדשים.
אבל מה המכניזם שמאפשר לך לייצר?
משום שיש לנו מבנה, שיש לנו תחביר, שיש לנו מורפולוגיה, אבל מספר החוקים של המבנה הוא סופי. עכשיו, זה דבר חשוב. עכשיו שאלה היא כמה אקספרסיב פעם, כמה משפטים שונים אני יכול לייצר, או כמה משמעויות שונות אני יכול לייצר עם אותם חוקי תחביר. זאת שאלה לגיטימית, אבל השאלה המעניינת זה לא כמה, אלא באיזה קצב זה גדל. כן, השאלה היא באיזה קצב אני יכול לייצר משפטים משמעויות חדשות כפונקציה של השפה שאנחנו מדברים.
אבל אתה עדיין...
זה אני יכול להגיד גם על מוזיקה, לא חושב שזה שפה. אני יכול להגיד כמה צירופים חדשים של צלילים מופיעים ביצירות מוזיקליות, וגם זה גדל אקספוננציאלי.
אבל יש שפה צריכה להיות מובנת.
ואני יכול להגיד על ציורים, ואני יכול להגיד על ריקודים של דבורים, אני יכול להגיד על הרבה דברים, זה לא מה שמייחד את השפה האנושית. זה לא מה שהופך את זה כל כך מיוחד. כלומר, אני יכול, זאת אומרת, יש לנו מוזיקה, יש לה הרבה תכונות שנראות כמו שפה, אבל היא לא שפה. היא לא באמת את כל התכונות של השפה, אבל היא במובן הזה של מספר הצירופים, זה גדל אקספוננציאלי. לא, זה נכון לגבי כל דבר כמעט. כל דבר שיש בו איזשהם אלמנטים שחוזרים על אותם בצורה סטוכסטית, אני מקבל מספר אינסופי, זה בדיוק משהו של אנטרופיה. אנטרופיה זה קצב הגידול של הספרות במקום שלי, הספרות השונות במקום שלי. זה מה שזה אומר. אם הייתי מתכנס מספר סופי של ספרות, אז האנטרופיה הייתה 0. אז זה שלאנגלית יש אנטרופיה, זה בדיוק כמו של אטומים במשחק יש נקרא. כלומר,
מה כן מייחד?
זו שאלה הרבה יותר מעניינת. כמובן שחלק מהייחודיות של השפה זה במבנה, באותן הסתברויות ניתנות. בקשר במבנה הסינטקטי, במבנה המורפולוגי, במבנה הסמנטי, בלשנים לא אוהבים לדבר על סמנטי. לא, איך מילים נוצרות, אני דווקא מאוד אוהב לדבר על סמנטיקה, כי יש לי מנה סטטיסטית, זאת טובה של זה, אבל התחבירים גם כן מאוד דומים כמובן, ולכן יש לזה, והם כולם מוגבלים במורכבות שלהם. זו שאלה מעניינת אם זה נובע מהמוגבלות של המוח שלנו, או אם זה נובע מתכונות אחרות של העולם שלנו, לא של המוח. אבל התחבירים הם מוגבלים, כל משפט באופן בסיסי מתאר פעולה, נושא פועל ומושג, וזה בכל זאת נכון בכל השפות, כי השפה שלנו מתארת תהליכים שעוברים עלינו, זאת אומרת, את האובזרבציות ואת הפעולות ואת הזיכרון הפנימי. זה מה שמתאר. עכשיו, הדבר הזה נכון גם לגבי התנהגות של בעלי חיים, לא רק התנהגות של אנשים. כלומר, אנחנו מתארים או יוצרים מושגים.
יכולים לדבר על העבר.
גם זה קיים בשיחות של בעלי חיים. אנחנו נדבר. בעיה שלא יכולים לדבר, במובן שאת מתכוונת.
אבל אתה תספר לי משהו שאתה למדת, שאתה חקרת, ואתה תספר לי, אני יכולה לרכוש אותו בלי להיות שם.
אני לא רוצה להיכנס לדיון ארוך שאנחנו הולכים לדבר עליו הרבה בקיץ, שנקראות מפתיון, אני הולך לשם אותה על זה, אבל בין היתר להגיד שרק בני אדם יודעים לדבר על העבר והעתיד זה קשקוש. כלומר, זה...
לא אמרתי את זה, אמרתי שזה מייחד שפה, ושאלתי איך אתה מוכיח שזה... יכול להיות שלא?
אני אגיד, תהליך מרקוב הוא חוק מאוד מהמורכבות של השפה. יש פה קורלציות אינסופיות ארוכות לעבר ולעתיד.
דיברנו על חיות, לא?
לא, אבל מודל מרקוב חבוי הוא לא מודל מספיק טוב בשביל לתאר שפות, כי אין בו ריקורסיה ושום דבר מספיק. עכשיו, אבל אני לא צריך מודל מסובך כמו המודל הריקורסיבי של השפה, בשביל לדבר על תהליכים של זיכרון ארוך. זה נכון, יש משהו נכון מה שאת אומרת, אני אומר את זה הרבה שנים כבר, שבאמת מה שמייחד אותנו זה טווח, לא עצם העובדה, כמה אחורנית בזמן אנחנו יכולים לדבר, כמה רחוק לעתיד אנחנו יכולים לחשוב וכמה רחוק לעבר אנחנו יכולים לחשוב. אבל מה שקובע את זה סוג של, כאן באמת את התמונה הרקורסיבית, כן, בצורה מאוד מאוד עמוקה, אני יכול לפתוח סוגריים, להגיד עוד משהו לפתוח סוגריים, להגיד עוד משהו וכן הלאה. אני לא צריך לעשות את זה אינסוף פעמים. במוזיקה יש הרבה חברות רקורסיות, כלומר,
זה התכונה של...
זה לא העניין, זה אפילו חוסקי.
כן.
אבל, זאת אומרת, אפילו חוסקי, הרבה דברים לא מסכים איתו, וזה אני כן מסכים איתו. כלומר, יש...
אבל אני אמרתי, אני חושב שאני יכול שיוסי חושב שרוסי חושב שזה רקורסיה.
נכון, אבל זה סופי. הכוח פה זה לא האינסופיות שלי. הכוח זה העובדה שאני באמת יכול בקלות יחסית לייצר משמעויות חדשות על ידי רקורסיה. אני יכול לייצר משמעויות חדשות גם על ידי יצירת מילים חדשות. וזה בדיוק הסיבה שאני לא אוהב לדבר על זה. כי ההגדלה של הסמנטיקה עובדת נגד הסיפור הזה שהרקורסיה כל כך חשובה. זה לא עובד נגד. זאת אומרת, אם באמת אני מייצר מילה חדשה כל פעם, כבר שאני אשתמש במילה הזאת, אני לא צריך את כל הרקורסיה, כי הכנסתי את המילה חדשה. עכשיו, לא יודע, נכנסתי למשחק שאין סיפור שלהם תוך מילה חדשה, אז זה גמרתי עם רקורסיה. זאת אומרת, אם הייתי יכול כל פעם שאני... לא, אני עכשיו אומרת, דני הלך לאכול ארוחת בוקר בבית ספר, כמו בכל המשפט הזה, עכשיו קורא לו גוגו, ועכשיו כל מה שקורא גוגו, את חושבת על דני הלך לבית ספר, אז סגרתי את כל הרקורסיות, צמצמתי את זה מאוד חדש. כלומר, במקום לייצר רקורסיות בגרף קיים, אני מגדיל את הגרף, מגדיל את מספר הנוד, וזה שקול גם עוד רקורסיות. אם אני מרשה לעצמי לייצר נודים חדשים בקצב לא גדול מדי, אז אני משיג את כל מה שהשגתי עם רקורסיות. מה זה רקורסיה? רקורסיה אומרת, הנקודה הזאת אתה יכול לפתוח מאמר מוסגר, ומכאן ואילך לחזור אחר כך הלאה לאותה נקודה שהיית לו קודם, כאשר מאמר מוסגר הזה הפך להיות אטום באיזשהו מובן במשפט שלי. כלומר, איזשהו סיפור שסיפרת על המשפט שם בעצם, עכשיו אני אומר, במקום לחשוב על הרקורסיה, אני המצאתי מילה חדשה בשיטה.
זה מה ששמעתי בשפה?
כן, בהרבה מאוד מקרים. זה מה שאמרת קודם. עצם העובדה שמילים חדשות
איך
נוצרות,
אתה לוקח רעיון שיש לו מבנה רקורסיבי והופך אותו לאטום?
למשל, המציאו דבר שנקרא תורת הקוונטים, עד שלא קבעו את השם הזה, תורת הקוונטים, תורת טבעית לגמרי, אז היה סיפור מאוד ארוך. מאותו רגע שהייתי לחזור לאטום 3 פעמים, קראתי לו בשם. ומאותו רגע המושג הזה הפך לחלק מהחכם. עכשיו, קודם לא היה. כל הזמן אני ממציא מושגים שהמטרה שלהם
אני רואה את הקשר של זה לרקורס. אני מבינה מה שאתה כל הזמן מייצר
מה הכוח של
חדשים.
רקורס? הכוח של רקורס זה באמת שאני יכול לכאורה לפתוח סוגריים הרבה פעמים. אבל קודם כל אני אומר שבאופן מעשי אנחנו לא חושבים אותו הרבה פעמים. אנחנו חושבים 3 פעמים ברוב המקרים, מקסימום. הרוב בני אדם לא מדברים ברקורסות של יותר מרוב 3, אז לא יכולים לעקוב אחרי זה. הזיכרון הטווח שלהם, הארוך טווח שלהם, לא מאפשר להם. אז באופן אינהרנטי אנחנו מוגבלים בעומק המשפטים שלנו. עכשיו, אז להגיד שהכוח, רק כשאנחנו אנחנו לבני אדם שאנחנו מדברים משפטים אינסופיים, זה פחות משפטים.
מקבלת את הרקורסיות,
לא,
המייצגת של
לא, אם היינו יודעים לדבר משפטים סופיים, לא היינו בני אדם, כן היינו בני אדם מאוד, כן, אנחנו מדברים משפטים סופיים. עכשיו, העניין הוא אחר לגמרי, העניין באמת פשוט לא מאוד חשוב באמת שהסיפור הזה שהוא עומק הזיכרון ועומק המחשבה לעתיד. אבל אותו אני יכול לכמת במושגים אחרים, גם במושגים של רקורס. אני יכול לכמת אותו במושגים של באמת predictive information, כל מיני כאלה שאני מדבר עליהם. זו שיחה מאוד מעניינת ואני אשמח לעשות אותו באיזושהי הזדמנות, אבל לא עכשיו.
לערוך כל מיני דברים שאנחנו לא מבינים. I asked him, he didn't reply yet. He didn't reply. But if you're going to give me extension to Sunday so it doesn't work, I'm not going to finish it. I'm not going to... Just what? Thursday? I didn't. I usually go to sleep straight away and I wake up straight away.
Okay, so we want to continue with a new topic which I mentioned last time and we didn't have time to dive into it, which is the notion of data compression. Or another word for it is codes, but let's leave it to be clarified later on. So I'm going to ask, so we have variables, okay, we have our famous x, which at this point can take a finite number of it's actually countable number of possibilities, it doesn't have to be finite, but I want to encode it by a sequence of symbols taken from a finite alphabet. And without losing generality, it's enough to think about binary sequences. So essentially, I'm going to, so let's say that I have an alphabet, let's call it, this is clearly A, which I never write correctly. So there's an alphabet. Alphabet finite. So let's call these elements, just for the simplicity at this point, as A1, A2, and so on, up to some AK. So this is a finite set, and as I said, without loss of generality, we're going to think about just 0 and 1. So this is a finite alphabet in some symbols, and so this is going to be, and the code is so a code, and this is a definition if you want, is a map, definition of something which I want to call a code, a code of x, of a variable x, a random variable x is going to be a map from x to finite strings of this alphabet. So this is so let's call this sigma, and this call this sigma star. So it's a bit confusing because sigma is used for many other things, but that's the way it's usually denoted in computer science. So there is an alphabet, and I'm talking about. So you can think about the sequences of some size k. No, not this k, some size n. So these are finite sequences. And I can think about all the sequences, not necessarily bounded sequences. Okay, this is for you more. Okay, so all the possible finite strings, in the alphabet in this A. Okay, this curly A. Okay, so for example, bits. So I have 0, 1, I have 0, 0, 0, 1, 1, 0, and so on. And 1, 1, whatever. 1, 1, this up to size 2, and length 2, and so on and so forth. Okay, so up to some size L, there are 2 to the L possible sequences in the alphabet 2, and K to the L in the alphabet in the general case. Okay. So when I talk about strings, I talk about strings like this. Okay. So a code is going to be a map of x, a map C, let's call it, from x to these sequences. So for every x in x, I'm going to map it into something which I call Cx, which is in this strings, finite strings over the alphabet. Okay. So a code, a particular code is a map to the string. So for every x that belongs to my variable, every value of my variable, which may or may not be finite or even may be uncountable at some point. So at this point, I want to encode by strings. Okay, so just to give you an example, let's say that my variable can take the values a, b, c, d. Has only four objects. So something like C of A is 0, C of B is 1, C of C is 0, 1, and C of D is 1, 1. This is an example of a code. Okay? So when I say 0, 1, I don't mean the number, I mean the sequence, the string. It also has a numerical value, but I don't care. Okay? So it's the string of letters, it's an ordered string. Yeah. Okay? So now, the interesting question is, and this is going to be a new characterization or a new property of entropy, which is going to be extremely important for us. That yes.
In your way of defining A, B, C, and D,
These are the objects of X. So X is this set, okay?
And what is A?
Something. Which A?
No, the
curly A? This A?
Yeah.
So this A is a set of alphabets. It's different things. And I said that the code is a map from the object of X to the strings of the alphabet.
So is A1, A2, is it a member of sigma or a member of X?
So these are member of X, and the strings are member of sigma.
Okay, but the way that you wrote it above, the A1, A2, AK, above? More
Here?
More above?
More up here?
Yeah.
So no, the one I'm just talking about the alphabet, and without lots of generality, I'm going to restrict myself to binary alphabet unless said otherwise. Okay. So from now on, the A's are either 0 or 1, and there are only two.
They are a member of sigma.
And no, sigma are all the strings. Yeah, they're a member of sigma, but I am actually usually put an n here, which is all the strings of length n. So which have k to the n, or in this case 2 to the n possible strings. Yeah. Okay. I don't have to explain it. Okay. So now there's one very important property of a code. We want to extend it in some sense. I want to extend it in the following sense, that if I have a sequence of symbols, not only one. So let's say, so I have a code, okay? So I have a map that for every symbol assigns a string. But now I want to use it to encode sequences in some sense, okay? So as you already saw here, I didn't even elaborate it, that I assume that the code is different for each all elements. Of course, I could code all of them by 0, but this is not a very useful code. I mean, it's not going to allow me to decode it in some sense, to go back to the original sequences. So I want to extend, what we call an extension of the code. So I want to be able to build from it a code of a long sequence of objects. Okay, so a long sequence of objects. So, for example, okay, if I have codes for letters in the alphabet, in let's say in English, so I have 26 letters. I don't care about case upper or lower at this point, and so we can encode them by bits. Okay, but so I need 5 bits are enough. Okay, because 2 to the 5th is larger than 26, so I have enough code words. Okay, but now I actually want something much more important. I want to extend the code, so I have a sequence of, let's say I have a word, not just one letter, and I want to encode the word as a sequence. So usually what we think of when we talk about extension is what we call concatenation code, which means I'm going to assign this to CX1, CX2, and maybe I put a small circle here just to indicate that I'm concatenating the sequences. Okay? So this is concatenation. Concatenation means I just בעברית אני משרשר אותם. I put it one near the other. Okay? So you know what is concatenating of a string. Just write it one after the other. Okay, so in this case, let's say I want to, if this was my original code, I want the code for A, B, C together. What will it be? It will be 0, 1, 0, 1. But you already see there's a problem here. This is not what we call uniquely decodable. Okay? Because this can be A, B, C, or it can be A, B, A, B. Okay? So, in other words, there's no unique way of what we call parsing it. Or parsing means, okay, I know that this is A, and then I know that this is B, and then I can think about it, either put a comma here and call it A and B again, or put a comma here and call it C. So there are 2 ways to parse this code, this sequence. It's not uniquely decodable. That's a problem, because you actually really want to encode long sequences by concatenation. So this little circle here is, again, concatenation. So I don't want new symbols. I don't want to put commas. This will extend my alphabet. So I want to keep the original symbols, but still be able to uniquely decode them. Okay, this turned out to be a very important non-trivial property. So I want the code, the extension, to be uniquely decodable, which means there should be one way of breaking this into the original sequence. So there can't be. So how would you formally define it? So I already said that a code is a function. It's assigned a single. It's a one-to-one function of the letters. But now I want to be a one-to-one, and this is what we actually call in formally we call it a non-singular code. So a singular code will be something which maps 2 different things to the same sequence. This is not good. Okay, this is singular. But if I want the code to be uniquely decodable in any extension of it, then one way of saying it is that the code of the concatenation code is also non-singular. Okay. So we want the concatenation to be one-to-one in some sense, or to be non-singular. And that's again, I'm doing it very, very quickly, and that's why I have to skip rigor, but it's all right. That's not new. Okay? Everything can be done much more rigorously, but I don't believe that it's helping.
What do you define as non-singular?
So singular is something which is not uniquely, it's not one-to-one, which means I'm mapping two different objects of X to the same string. So it's not decodable at all. It's not, even on a single letter value, it's not decodable. So this was a non-singular code on the letter value, because each symbol has a different string. This has 0, this has 1, this has 0, 1, and so on, or 1, 1, whatever. You see that this is the problem. You see this problem here, that 1, 1, for example, could be BB, or could be D, and so on. So a singular code is a code which is uniquely decodable. Once I see the string, I can go back to the original symbol uniquely. I have no confusion. Okay? If I want the concatenation or the extension of the code to be non-singular, it turns out to be a non-trivial property of the code. Okay, so for example, one way of making non-singular codes is like we do in natural languages. We actually put spaces, or something like this, spaces or punctuations of some sort, to separate the strings. So words in language are codes in that sense, and usually it's non-singular. Of course, it's not true for natural languages. For example, we have words in Hebrew that without nikud, how do you say it, punctuation, are singular. You can read them in different ways. So this is not a very good code there. But even in English, we have different words that have exactly the same code, but different meaning. So we need to see the word, I don't know, fire. In English, it can be a verb, it can be a noun, it can have different meanings as verbs and different meanings as nouns. Okay, so the natural languages are very bad codes in general. Okay, but so now we want to be careful about it. This is the end concatenation. So we want the concatenation or the extension of the code to be non-singular. As I say, one way of doing it is introducing a separator, like space. But as you may know, I mean, actually languages in writing had no spaces until very late. If you look at not very ancient Hebrew, just 2,000 years old, had no spaces. You didn't care about it. You could read it any way you want. Okay, so Latin also, by the way, it didn't have spaces. This was a new invention. So something similar to the invention of the zero in numbers. Okay, so what is the condition for what we call uniquely decodable codes or uniquely decodable extensions of code? So I want to be able to parse it uniquely, any sequence. Okay, so I'm just thinking if I want to prove this now or at the end of I'll prove it now. So there is something called this is a theorem. It's actually usually known as Kraft inequality, which again turns out to be a very important property. So before that, I need something else. So every code has what we call a length function. So the length of the code of X is simply defined as the length of the string. So and this is just a notation again, which is a bit confusing because this is not an absolute value. In this case, it's the length of the string. Okay, so we are talking about finite codes, finite length code. So there's always a length. So this is what we call the length function of the code. Okay, so for every code there's a length function. Simply the list of lengths of the code. So in this case, what is it? This is 1, 1, 2, 2. Okay, so the length function is simply the length of this. Very simple. Okay? So the Kraft inequality, which is quite a remarkable statement. I mean, it's something surprising. This was surprising to me at least, and not only to me. A code is what we call uniquely decodable. Uniquely, what do I miss here? Another F? No. Unique, yeah. Uniquely decodable. So this is essentially a definition. I just gave it here, which means the extension is non-singular. And non-singular means that it's not one-to-one. So a code is uniquely decodable if and only if, I write it here explicitly that you understand how important it is, its length function which means the set of lengths for all the x's in X. Again, the length function is the absolute value of the code, the length of the code. So this set of lengths is what we call the length function. So this is just the length of the string. So somebody knows it? I'm sure somebody knows it. So what is the condition? The condition is that the sum, I'm talking about binary alphabet now, A1 and A0, and A2 are 0, 1. Otherwise it's the size of the alphabet. 2 to the minus Lx, sum over all x's, is less or equal 1. Okay. If and only if. So if the code has this property, which means the length of the strings of the code, the sum of the, and in general, if this was not necessarily a binary alphabet, so this is the size of the alphabet here. Okay.
L of x is actually L of C of x, right?
Yes, I just studied. L of x is the length of C of x. This is just my definition, just not to write L of C of x. Yeah, so this is L of x, yeah. Okay? So this is the condition. The sum of the 2 to the I'm talking about binary strings, and as I said, this is completely general. If it's not binary, then it's k. Okay, the size of the alphabet. If and only if, so a code is uniquely decodable if and only if this function is less than 1, less or equal 1. Okay, this is a remarkable theorem. I mean, I always think that this is a very clever statement. But before I prove it, so I'm going to give you 2 proofs. One is I want to say that there is no uniquely decodable code which doesn't obey this. But I'm going to restrict myself to a special type of code first. Yeah. So this here, I want to continue somewhere. So example of non-singular codes, or uniquely decodable code, I'm sorry. So example, before I prove the theorem, is what we call suffix or prefix codes. So what are suffix codes? Suffix codes, בעברית קוראים לזה קוד רשע וקוד סיפא, אני שמות מצחיקים כאלה. Suffix code. Or prefix code, it's essentially symmetric. Do I need a double S? Probably not. Prefix, suffix came with prefix law. So prefix and suffix, so essentially every string has substrings. Okay? So if I have a string A1, A2, and so on, up to, let's say, size L of X, so this is, let's say that the code of X is this string. Okay? So a suffix of the code is going to be some tail of the code. Okay, so for example, A the last one is a suffix, and then the next two is suffix. Any tail of the word is a suffix. Okay, and the prefix of the code is some head of the code. So these are going to be prefix heads, if you want, in some sense. And these are some tails, okay? So any tail, any subset of the string, which is the end of it backward, or the beginning of it forward, is a suffix or prefix, okay? Now, what we call a suffix or prefix free. Suffix free code is essentially a code that no suffix of its code words is another code word. Okay? Or no prefix of its code word is another is a prefix code. So for example, the code that I wrote here before, which caused me problems, where is it? Oh. There. This code 010111 is neither suffix nor prefix free, because you see that the code 01, its suffix, the only suffix here is 0, and the only prefix is 0, which is another code word, and the only suffix in this case is 1, which is another code word. So this is not a free suffix, no prefix free code. So suffix is a subset, it's either the tail or the head of the sequence, some tail. So any subsequence, which is either at the end or at the beginning of my sequence, is called a prefix or a suffix. So for example, in Hebrew we have the word aleph bet, which is the av, and we also have the word abba. Actually related, but it's a different word. And there's also the word baf, which means it's a very bad, it's a very bad suffix code. Suffix or suffix, prefix, it's really bad. I'm sure there are examples in English. Okay, so natural languages, words at least are not suffix free or prefix free. But suffix free codes, let's say, concern ourselves to actually suffix free, and what is really nice about suffix free or suffix free codes is that I can map them to trees. So suffix free or similar prefix free. So prefix free codes are uniquely decodable. Uniquely decodable. So this is a statement I need to prove. And the way we do it is by mapping them into trees. So essentially, let's say that a suffix free code, a suffix free code. So the statement is just another small theorem that any suffix free code, any suffix free code can be mapped to leaves of a tree. Okay, so you know what the tree is already. So essentially, which means it's actually not only a tree of in the alphabet. So for example, this is a binary tree. Remember, we have a root, and we have if it's binary, then the splits are always binary. So essentially, what I do when I write a binary tree like this, I think about this branch as a 0. Whenever I have a branch, I put 0 to the left and 1 to the right. And then I'm telling you, okay, this is a leaf, this is a leaf, and this is a leaf, and this is a leaf. A leaf of a tree, in this case, it's a tree growing backward into the ground. That's what we call leaves. And so this is there are actually, in this case, 4 leaves. Okay? And now I'm telling you that if I use the length along the tree as the code word, this is going to be uniquely decoded. Okay, so for example, this is going to be the C of A, this is going to be the C of B, this is going to be the C of C, and this is the C of D. So what it means, what is the code? So C of A is 0, as before. Okay, C of B is now 1, 0, 0. Okay. So the leaf, when the code is the path from the root of the tree to the leaf. Okay, so this is again the root, as nothing. So in this case, C of B is 1, 0, 0. And C of C is what? 1, 0, 1. Okay. So I just want to make sure that you are with me. 1, 0, 1. And the C of D is 1, 1. Okay. So this is now a suffix-free code for my 4 letters. Is it clear? Now, is this uniquely decodable? Well, you see immediately that it is. Because if my code words are only on the leaves, which means this cannot be a code word and this cannot be a code word, only the leaves are, no suffix of any code word is a code word. Okay? So if my leaves are on a tree, or if my code is on a tree, it's uniquely decodable. It's suffix-free. It's not yet clear it's uniquely decodable. But I'm going to state now that suffix-free codes are uniquely decodable. Okay? Yes?
Also the prefix 3.
Yeah, the prefix I have to call I simply interpret the tree backward. Instead of the beginning, so this is the end of the last letter, and then I push it.
Is that true for the tree codes that other people can be back to the tree? It's also true for it can be back for us.
So both suffix and prefix free codes can be mapped to a tree. The only difference is that in one case I read it from top down, in the other case I read it backward. That's the same thing. Okay? So I start, and instead of, if you think about it as this was the last letter, and then I push it and then put another one, another one. The question is, how do you extend the code? Doesn't matter. So prefix and suffix trees are completely symmetric. For any prefix tree, there's a one-to-one dual suffix tree, completely one-to-one related to each other. So it's enough to talk about suffix trees or prefix trees, whatever you want.
Is it the suffix of C of B?
It's actually a prefix tree, the way I wrote it. Prefix tree. Okay? No sequence is the prefix of another sequence. Okay? Of another code. Now, why is it uniquely decodable? Because if I had now think about this, any string of bits in this case. 0, 1, 1, 0, 1, 1, 1, whatever, 1, 1, I don't know. My random number generator got stuck somewhere. Okay, never mind. It's any sequence of bits. How do I parse it into code words? Well, I go to the root of the tree at the beginning, and then I see 0, I move here. If I go to a leaf, I put a comma. Now I go back to the root of the tree. I see 1, 1, 0. Okay, not enough. 1. 1, 1, 0, 1. Okay, so here it is. I go to leaf. Now I go back to the root. 1, 0, 1, 0. So 1, 0, 1. Okay, 1, 0, 1 is enough. I put a comma. Whenever I get to a leaf, I put a comma. Now, since this is a unique process, you always get to a leaf eventually, because the tree is bounded. I mean, there's a finite. Even if it's not bounded, I always get to a leaf with high probability at some point. Okay, we are going to talk about infinite trees, but not now. So this is uniquely parsed or uniquely decoded. Okay.
What about the redundant cluster? I mean, you have this 1.
0, 1, 1, 1. No, maybe I didn't finish the code. I mean, you can have, by the way, things in the tree which end up nowhere. So I mean, okay. Actually, in this example, I used all the lists of the tree as code words. But I could, for example, have another. Ignore this one. No, in this case, I had only 4. So not all the lists have to be. I never said that all the lists have to be code words, but all the code words have to be lists. Now, if I have lists that are not code words, then there's something there which I don't know how to decode. I mean, I just go to the list, but then when I go to the list, I go back. So there may be some nonsense in my screen. Right.
Talking about this example that you have 1, the 1, and you have a list for 1, 1, but you have this one there, the first one.
This one?
No.
No, I'm not sure. This
First
one?
number one, yes.
Yeah. So now, so
It's not assigned to any.
no, but it's here. I'm back to the root. One, I didn't get to a
You
leaf.
go back to.
I always go after a comma. I always get back to the root. This is the algorithm. See the tree. Whenever you get to a leaf, you put a comma and go back to the root. Okay. So I'm going to run through passes of a tree, which eventually is going to end somewhere. Okay. Hopefully. Yeah.
This code is very sensitive to noise, right? So if one bit change or I need.
You're absolutely right. We're going to talk about it much later. Yeah, this code is if I switch one bit, I'm going to make mistakes. Not only in this word, I'm going to make mistakes all over. One bit, switching one bit here is going to change my decoding from there on. So you're absolutely right. That's a very, very good observation. But we'll come back to this. Okay, much later when we talk about error correction codes. So at this point, I'm just trying to build the basic concepts, and I'm almost out of time. So you know, I'll keep the craft inequality for the next class because it's going to take me at least 10 minutes to prove it. I'm going to have to show you something quite important about entropy already. So remember, we had this asymptotic equivalence property. Now what I'm going to say now is going to be a little dense, so pay attention. So essentially, imagine that I care only about the typical sequences of I don't care about. So I'm actually saying that the fact that there is a finite entropy is allowing me to have a uniquely decodable code of length how much? Okay, so let's look again before I prove the Kraft inequality. When you actually prove it yourself that a suffix or a prefix 3 is obeying the Kraft inequality. This is really a very simple exercise. It's not very simple, but it's a good exercise. Try to do it. I'll do it next time in a much more general way. But I want to say something about codes and asymptotic equipartition. So only from the asymptotic equipartition property of sequences, I already see that the entropy has something to do with the length of the code. Okay, so remember, imagine now that I have long sequences and I'm assigning, so I know that the probability of the typical sequences is more or less 2 to the minus n, h. Okay? So the probability of the typical sequences, what can I erase here? So the claim is, or proposition, or whatever you want to call it, is that if there is a finite entropy to my source, my random variables, then I can actually compress them. So of course, if I want to compress everything by, if there is a finite number of possible strings, then I just have to find n large enough such that 2 to the ln is larger than the size of my variables. Okay. So essentially, I'm going to assign what the statement is that if I take L of x to be essentially for all the typical sequences. So remember, this is an extension. So I'm now going to code an extension of my code, a long sequence of my code. And this is why it's a bit abstract what I'm saying now. So I'm going to encode a sequence, but even not necessarily as a concatenation code. I'm just going to encode it by a unique sequence. And I'm saying that